All right. Good morning, everyone. Let's get started. Do you have any questions before we begin? All right. I think I have a. All right, cool. So there's no question. Then let's continue with where we left off last time. So last time we started discussing 8.7, order statistics. Okay. Yeah, so to remind everyone of the setup. So again, we have IID sample. Here, we do not assume any particular population distribution, but we do assume that they are continuous. All right, so from a continuous population distribution, and popular choices, uniform or exponential. These are the so-called toy example, because they are very easy to deal with, or at least they're easy to plug in. But the more complicated examples would be something like I don't know, gamma or something, or beta, but the densities there are a little bit harder to manipulate. All right. So we have this IID sample, and then we would rank them. If we rank and order them, then we get the data in the order of smallest to largest, where the one with the parenthesis will denote the min, and the n with parenthesis will denote the max. The textbook would use this notation. Okay. So, and as I mentioned last time, I will stick with this notation. Okay. So just to, again, I think many folks are still, I've seen students making mistake about the notation all the time. So let me give you an example. So let's say we have a sample like this. 5, 10, 2, 1, 6. Okay. So there, right? If this is our random sample, then this will be, right, x1, x2, this is x5. Okay. But obviously, right, if you order them, then there will be 1, 2, 5, 6, and 10. So the minimum value, x1, is 1. The maximum value, x5 parenthesis, is 10. Okay. So the point being is the first value of the sample and the minimum don't have to be the same value at all, or they're only the same with the probability of 1 over n factorial or something. So, or maybe 1 over n. So anyway, right, do distinguish these two. So our goal is to understand, right, to derive the sampling distribution or, for that matters, right, the density of the order statistics. Okay. So let's begin with actually let's kind of play around with this idea a little bit in terms of population distribution. So first of all, there's the idea of what's the use, okay, of order stats. Okay. I mean, you can use order statistics in many ways, but in this course, as I allude to, the generic context is you have some unknown parameters from the population distribution. So suppose that you have x1 up to xn, IID, uniform A to B, AB unknown. All right. So your goal is to be able to say something about the parameter A and the parameter B. Well, you don't know anything about them. So a natural estimator for A, okay, we call it A hat, would be the minimum value of your sample. And similarly, a natural estimator for B would be the maximum value of your sample. Is this clear? I mean, when I say natural, I assume that you see it makes sense that we use this as a guess for the max and the min of the population distribution. Okay. So, well, I mean, it goes without saying, but let me ask you this, right? What are we talking about? You mean so far or right now? Oh, rewatch the lecture. Okay, it's recorded. So, for example, what is the, in this case, what is the population max and population min? This is an obvious question, but I hope you see, right? What is the what is the population max and what is the population min? In this example. Yeah, no. So first, right, Derek, when you do X, those are the sample. When we say population, yeah, obviously just A and B, right, or B and A in that order. Okay, so these are exactly straight from, right, when we use the word population, right, this is just straight from the population distribution or the, right, when you understand. So there are two levels here, right? The theoretical level, the model level, where again, right, these are unknown parameters, but they're constants, okay? Unknown but constants. Some mysterious constants. So A hat and B hat are the estimator for the population values, right, Samuel? They are not. So yeah, you're saying something about the relation between A hat and B hat and B. In that regard, I think you're correct. But when we, I mean, again, just terms, right? When we say population max, we just mean that mysterious value of B that we don't know. Okay, but sample max, right, is A hat. Sample min is B hat. Or no, sorry. Okay, sample min is x1, sample max is xn. And then you use this as estimator for A and B. Okay, these are what these notations mean. So basically, yes, you use the sample min, right, as an estimator for population min. You use a sample max as an estimator for population max. Okay. I mean, again, it goes without saying, but suppose you have something like this. Let's say IID exponential lambda. What is the population max and population min in this case? if you have exponential distribution, then what's the population max and min? Yeah, so you can say it does not exist here if you want, right? I mean, we do not think of infinity as a legitimate max, right? But the min exactly is 0. Correct. It's fine, right? But infinity is not wrong. I understand what you're saying, but I would not count that as a max. But yeah, so the point being, right, you see that in this case, for example, the population max, sorry, does not exist. There is still a sample max, right? Sample max is still there, something like this. It's just the maximum value of your sample, okay? You can still have your sample min in this case. So the concept of, right, sample max and sample max and sample min is connected to population max and min in some way, right? But they, in terms of statistics, they come to life, right, when you have a bounded support. Support means the values where the density is non-zero, or support means where the random variable takes value, okay, where the distribution takes value. So in an exponential distribution like this, because I guess the population min is assumed known, right, it's 0. Probably you don't care so much about these values as statistical estimators. But I mean, of course, you can still discuss, right? I mean, the properties of the sample max and sample min, etc. Okay. One more thing. So suppose, right, you have, let's say, you have a sample x1 up to xn, right? And let's say n equals to 5. No, got to be careful. No, I think the term finite and infinite population are refer to something else. Okay, finite support, but finite is a different word. Finite population in the book refers to sampling without replacement, meaning when you pull one sample, right, you will influence the next sample you pull from the finite population. That's not the same concept. I mean, that's not the same word, right? What you have in mind is finite support, meaning the values that the population can take. It has nothing to do with the size of the population. Yeah. I mean, by the way, right? We always discuss infinite population in this class, meaning independent sample. We do not discuss, I think, 8.3 or something like that, which is finite population. All right. So back to the sample size, n equals to 5. Okay. So x3, right, is the median. I hope that's clear for, right, everyone. So in general, right, suppose that n is 2k plus 1, right, 2k plus 1, the book used m to m plus 1, then x, let's see here, xk plus 1, right, is the median. Okay, for the odd size of sample. Is that okay? So this is another order statistic that we care about. Now, what role does the median play in, things? So let's go back to some example. Let's say we have x1 up to xn, IID, uniform AB. Okay. So by the way, when we discuss the median, to make things simple, we always assume odd sample size. Okay, we always assume odd sample size so that the median is one particular value in the sample and not the average, okay, of the two middle ones. So suppose you have a uniform AB distribution, then what is the population median? What is the population median? b plus a over 2, right? Not b plus 1, right? But b plus a over 2. That's correct. Okay. So another example. Let's say IID normal mu sigma square. Then population median is mu. I hope that's clear. Well, what about IID exponential lambda? What's the population median? Wrong. The median most of the time exists. Not lambda either. Not lambda either. All right. So I bring this up because I guess I didn't even clarify, right, what it means here, even though these answers are correct. But what do you have in mind when you say it's a median? So you have to ask yourself, right, what does the median mean? The median, right, by the way, usually the median for a abstract distribution, the population distribution, the population median, the abstract notation for it would be denoted as mu tilde, okay? In contrast to mu, which is the population mean. And mu tilde would satisfy the properties that the probability that x less than or equal to mu tilde would be 1/2. That's what you mean by population median, right? And now that translates to when you have a density, this statement, 1/2. Okay. And here you see the relevance of us assuming a continuous distribution. The reason is, for example, if you have a discrete distribution, then there's no exact value for the median, for the population median, for example, among other things, right? But for a continuous distribution, there's always an exact value such that, right, half of the distribution is below it and half the public distribution is above it, okay? So in this case, all right, so why could you come up with this example, these answers very quickly? Obviously, you were giving the answer as mu, right, as the population mean. But the reason why you could do so is because these distribution are symmetric, correct, around mu, meaning the population mean, right? But because they're symmetric, of course, 50% is below mu, 50% above mu, so mu and mu tilde coincide. Okay. But obviously, for a non-symmetric distribution, which exponential clearly is, right, that's not the case. Now, those who say infinity is not correct because obviously there is a value somewhere here where half of the area, right, under the curve up to that point, I mean, the area under the curve up to that point is a half. And for those of you who say lambda, also you should be wrong. I mean, unless lambda is a very particular value, because, right, lambda is the average mean. It may not be the value that a half, right, of the distribution is to the left, okay? So anyway, how would you do this kind of question for exponential lambda? Taking a clue from here, right? You would do the integral from minus infinity to mu tilde of 1 over lambda e to minus x over lambda dx to be a half. Oh, well, so here you don't have to do it for minus infinity, right? From 0. Well, that would be 1 minus e to minus x over mu tilde to be a half. Okay, if you integrate this, meaning, right, e to minus x over mu tilde to be a half, or mu tilde is natural log of 1/2, which is minus natural log of 2, right? So Oh, what am I saying? Minus mu tilde over lambda, I apologize. So minus mu tilde over lambda, right? So mu tilde would be natural log of 2 times lambda. Is this okay? Notice, right, because natural log of 2, wait, is it bigger than 1 or less than 1? I'm not so sure. I don't know the natural log of 2 value. But clearly, right, it's not lambda, okay? It's not lambda. Any question here? So, right, so back to what we have. We have a sample median, all right? We have a sample median. So the sample median is clearly is a natural estimator for the population median, okay? Whatever they are. Now, this gives an interesting question like this. Before, right, a natural estimator for mu is the sample mean because mu is a population mean. But now you have the population median, right, which will be estimated by a different sample statistic, namely the sample median. So, of course, in the case where they're different, right, then sample median and sample mean kind of estimate different things. But in the case when the population median and population mean are the same, then you have two competitive, like two competing estimator for this value. One is sample mean, and let me denote it like this: sample median. Okay. They both are legitimate estimators for the same parameter. Of course, when you have more than one choice of estimator for the same parameter, you would question which one is better and why. Okay. And again, right, to decide that question precisely, then the sampling distribution is what you have to look at. And so again, this justifies the whole idea of why you want to study the order statistics. Is that okay? So by the way, right, by the notation x tilde, I mean this, x tilde, I also mean this. Any question on the context? And then we're just going to do probability before we go back to statistics. All right, so let's start with the easy one. Sampling distribution of the max. Okay. So suppose that we have x1 up to xn IID with, let's say, population density f sub x. Okay. Now we form the sample max. We want to find the density of this guy. How would we proceed? How would you compute the distribution of a max of two random variables? Or for that matter, right? how do you compute the distribution of any random variable in general. Apologize. So excellent, Alex. Excellent, except that you got it in the wrong direction. It should be the other way around to begin with, right? Intuitively. I mean, well, not intuitively, but let's say you're pedantic, right? You just deal with the CDF first. But the CDF, no, it's fine, right? The CDF start with probability of this less than or equal to this, right? By the way, the CDF is bread and butter for any distribution, okay? I know that I did say density and distribution function, but the CDF, okay, at a more advanced level is the one that controls the distribution. So at any level, you go back to the CDF, okay? Now, then goes to what Alice was saying, that will be the probability of the max less than or equal to X. And actually here, correct, right? And then you follow logic, you get there. So, but so Young, you got that from a book, from your knowledge, or you know why that's true? What's the logic there? How is that? Oh, that's fantastic. If you know, again, right, by the way, feel free to quote from your knowledge. I have nothing against that, even on the exam. If it's right, it's right. Except then, you know, in the case where I ask you to derive it or something, then you cannot say because I know it. But otherwise, you need to use it, okay? As long as it's correct. But I like to understand where the knowledge comes from. And so what Youngyu was suggesting, right? So the big F, yeah. So actually it's from here. You see, that's what we're having. And what I was suggesting that, right, connecting with what Alice was saying, she wants to put the X here, which is okay, but it's not the CDF, which is not a big deal. The big deal actually is right here, where the logic will be connected with what Youngyu was saying, that because the max less than, right, this statement logically says the max is less than a particular value. That means, right, every single value in there will be less than that. Any single random variable in there will be less than that X value. Okay. Now you note that this is AND, right? This and this and this. So by independent, that will be the product. Okay. But notice the crux move where you rely on the max to get down to the the logical statement. Okay. So this is from independent, and now from identical. Okay, because they all have the same density. So you could, I guess, in Youngyu's language, do this, where, right, of course, F is the CDF. In terms of the PDF, of course, it's this. Also, in terms of the PDF. Any question here? All right. But notice our goal. So here, what have we derived? We derived the CDF of the max. Okay. So of course you want the PDF, right? So the PDF is the derivative of the CDF. That means you have to differentiate this guy. but that's just chain rule going on for you. So that will be n, and then differentiate the inside, but differentiate the population CDF gives you the population PDF. And that's exactly right, the formula that Young-Yu was quoting. Any question? Okay. So for example, let's say that x1 up to xn, IID uniform AB, right? What is the density of the max? Well, here's the formula, right? There's n, sorry, I missed an x here, right? Then you multiply with the probability that a generic uniform AB is less than or equal to x. Well, what would that be? That would be x minus a over b minus a raised to n minus 1. Then you multiply with the generic density of a uniform AB, which is 1 over b minus a. But be very careful here, okay? This is where students tend to make mistake with distribution like this. Can I finish with the density of the max like this for this case? Is this done? The answer is no, okay? Because actually this is not correct quoting of the uniform AB density. The uniform being a uniform is very special in the sense that it's a limited, right? It's a finite support distribution. So you have to write something like this. Okay, you know why? Because if you don't highlight this, when it comes to computing certain things, you will not account for that. For example, so first of all, any question on the density here? For example, right, suppose that I ask the next question, what is the expectation of your sample max? Okay, what is the expectation of a sample max? Okay, what do? Well, you do the integral, right, from a, sorry, so you do the integral, let's say, of x times the density. Yes. But again, I can totally imagine a student not paying attention, putting something like this in. Or worse yet, something like this in. Okay, what happened there? The person does not pay attention to where the support of the sample max is or where the sample max takes value. Right, x1 up to xn all comes from a uniform AB distribution. So the max itself, being the max of these values, right, cannot go beyond those. So the correct integration range must be from A to B. Is that okay? Now, let's carry this on a little bit. Let's suppose that I want to know what this value is, meaning I need to figure out this integration. This is a technical question because this technique only applies this question, but you need to deal with integration in general in this class, calculus, okay, as your TA would say it. How would you integrate this problem? For one thing, right? Oh, by the way, you don't have access to that on the exam, all right? I don't care what you do on the homework, fine. But on the exam, definitely no help from the computer in that sense. Yeah, I mean, we're just doing hardcore math. The right answer is you want to do a change of variable, u equals to x minus a. Okay, you definitely do not want to mess around with this n minus 1 power. Or I would do something like this, because I don't even need to do that. I would multiply and I would add and subtract x minus a. It's the same thing. Is that okay? So what happens is I see that to match up the x minus a here, that's all it takes. I subtract a here and I add a back for this term. Why so? Because, right, the first one will be just this. Let's pull the constant outside. What is the value of this integral? The value of this integral is a. Why? Because I'm integrating a exact density there. Right? This being the density of the max. If integrate, it must be 1. Okay. So then this comes to integrate this, right? You got raised to n plus 1 over n plus 1. So you got n, right? b minus a to the n plus 1 over n plus 1, b minus a to the n plus a, which is n over n plus 1, b minus a plus a. Any question? So, right, I want to do this example to demonstrate several things. First of all, right, you can definitely expect some question like this on the exam, meaning the whole point of discussing the density of the sample statistic as the order statistics is you want to be able to work with the density, all right? So this question did show up in my midterm at some point. And well, sure enough, students kind of stumble through it. But my point being is, right, I know that this looks like a scary integral to begin with. But awareness, right, of what you need to do and what you don't need to do is the key to unraveling any of this. I would say that these are pretty simple steps that, students in calculus can take. But of course, right, without the awareness that this is the density, etc., you might be in a nightmare without knowing it. So, okay, these calculations will be expected of you on the exam. So try to see and try to bring in the awareness in terms of this calculation. Now, why do I calculate this, right? A is a exercise in, like working with the density of the max, but B, right, it has statistical meaning. What is the, so right here is the expectation that the sample max. This comes from a IID sample from uniform AB. Remember the point of the sample max? The sample max is supposed to be the estimator for B, right? So let me say this. It's not like the estimator, is an estimator. Okay. Remember, I said, right, that I use the concept of being on target, meaning if you use the sample max, right, or you use a statistic as an estimator for a population parameter, on average, are you centered around that true value? Remember, this is unknown. So you use a random value to estimate an unknown value. It's probably comfortable for you to know that on average, right, your guess is at that value. And of course, the concept is called, right, unbiased. And let me just introduce that concept, right, that concept. So we say xn, right, or any parameter, any estimator, theta hat as an estimator is unbiased for theta if expectation of theta hat is equal to theta. That's what I mean by on target. All right. This is a, I think, chapter 10 concept, but it is nothing really serious, right? You have a sample statistic that's meant to be an estimator for a population population parameter that's unknown, is on target, right, or is unbiased if on average your guess, right, your sample statistics is equal to the true population parameter. That being said, is the sample max here unbiased for the population max? Is xn unbiased for B from the calculation? No, right? Because you can clearly show that this is less than B. Right, exactly, right? But because n over n plus 1 is less than 1, right? So A plus B minus A is less than B. Is that okay? So therefore, right, this calculation actually has a lot of meaning. It's not just a pure exercise in calculation. It shows you that if you use a sample max as an estimator for population max in this case, you will always underestimate, on average, the true population parameter. Unlike the sample mean, right, you will be on target. But here, right, you always underestimate. All right, so that's the meaning. So it's not unbiased for B. Okay. We will revisit these ideas later on. So, but I just want to show you the relevance of knowing the order statistics density. Any question on this? Also, right, it should be intuitive that this guy cannot be a unbiased estimator, or this guy should not be, right, unbiased estimator from B. Why so? Because the average of a random variable is equal to a value if, right, sometimes it's above and sometimes it's below. Okay. But if you're always below, you can see, right, if you're always below, then there's no way your average value is equal to this. That's what has happening here. Because you sample from a uniform AB, right? By definition, your values will always be less than B. So whatever the max is, it cannot even be, it can never be above B. So when you take the average, it will never equal to B, okay? So that's the intuitive argument. But the mathematical argument, if you want rigorously, is to go through this. And, right, it has the advantage, as Samuel was saying, that you can even know, right, you can say further that if you have a large sample, then the bias is not bad, right? The bias is not bad as the sample size goes to infinity. Okay, so I hope that's enough for the sample max. Let's turn our attention to sample min. So how would you compute the density of the sample min? So actually, right, I mean, let's see if those of you who are kind of good at guessing, the sample max, right, by, what we just derived or what, your friend was suggesting is this. Can you extrapolate 1 minus, probably you mean f, right? And differentiate, is that what that's what you're saying, not integrate and differentiate. Yeah, so you might expect, right, that would be 1 minus this raised to n minus 1 times the density with an n in front. Okay, I'll leave it as a question mark for now because that's our guess. But we can justify it. And by the way, right, the reason why I say you can guess this is because the logic, okay, the intuition of the derivation carries through. And that's what I want you to be able to get intuitively more than just staring at a formula, right? What is the intuition? The intuition exactly, right, like your friend said, that the max less than or equal to a value means every other values must be less than that. So this quantity is just us differentiating, right, the probability that every single value in the sample is less than x. The min, right, if you want to work with the min, you just turn the picture around. You probably would want to work with differentiating the probability that all value in your sample is bigger than x and differentiate, right? But so technically speaking, right, let's work out the detail rigorously, but that's the intuition. How do you work out this detail rigorously? Rigorously, right, now it's exactly what Alice was saying, that this probability is appropriate for us to consider. Why? Because this being the minimum of all these values, that would force every single value to be higher than x. By independent, this is the product. By identical, okay. Now, the density is the derivative of the CDF, okay? So be careful. This is not the CDF. This is the 1 minus the CDF. But actually, that's fine. It's just a sign change. So if you want, it could be minus of this. Okay? Which is minus differentiating this quantity which, right, you bring n inside, you got this to the n minus 1, and you differentiate the inside, you pick up another minus, right? Exactly with this rule. So you got the density. And if you want to use the language of the CDF, then this is going to be n, right, 1 minus a CDF. If you want to use the language of the PDF, there you go. Okay. But for me, right, these 3 points are the same. They kind of say the same thing. It just depends on what kind of information you have. You just plug in. But right, so the official answer, the official formula, I think we go with is this. Just make it easy. But right, the meaning is any one of these. X1, right? I don't want to write xi, x1, the minimum. Any question? Okay, so let's take a look at example. Let's say x1, sorry. Up to xn, iid exponential lambda. What is the density of the minimum, of the sample minimum? Well, so there's an n. Okay. There is the probability that you are above this value x. Well, what is it? So first of all, what's the density? The generic density is 1 over lambda e to minus lambda x, right? What about the probability that you are above a value x? So normally you might have to integrate, right, x to infinity of 1 over lambda e to minus lambda u du and plug that in. But the answer I know, right, is e to minus lambda x. Over lambda, right? So e to minus x over lambda. Raised to n minus 1. And sorry, right, here's x over lambda. I quote the wrong density. Okay. What range does the minimum take in this case? For the exponential lambda, what range does the minimum take in this case? The order statistics, right, takes a range in the same way as the population distribution. So in other words, here the range of the min is still x positive, x non-negative. Nothing changed in that regard. So if the population is from A to B, then the order statistics from A to B. Okay. If the population is from 0 to infinity, then the order statistics is from 0 to infinity. All right, let's clean this up a little bit. This is n over lambda. Notice this guy and this guy are the same, and this is just n minus 1. So you got e to minus nx over lambda, x non-negative. Oh, and by the way, I violate my notation, right? This is x1. the minimum, not the first value of the sample, the minimum. Okay. Any question here? And also, do you observe anything special here? Yeah, so if I were to ask you, what distribution does the sample minimum have in this case, what would you say? Oh, yeah, I think that's what you said, right? I got it. Very good, exactly. So the sample minimum here is not just any arbitrary distribution. The sample minimum here somehow is exponential as well. With Alice is at lambda over n, okay? Because we invert. That's why I was confused. We invert the 1 over lambda in the density. So lambda over n. Okay. So that actually, this calculation shows a very special property of exponentials. The minimum of independent exponential distributions is also exponential. Okay. I mean, that's a fact that would be useful when if you take a class like 478, stochastic process. Here, we don't really use this anyway, but it's a very interesting observation. The minimum of exponentials stay exponential. It's not true for the max, okay? The max of exponential is not exponential. You can, again, right, use the formula we derived above to get the sample max density, and you can observe that it's not an exponential distribution. So I think it goes without saying, right? If I were to ask you to calculate the expectation of the sample min in this case, what would you get? You should get lambda over n. Correct. And notice, right, if you, there's no estimation going on here because we know what the population min is. But, you can always, right, associate that in your mind. This clearly is above the population min, right? I mean, lambda is positive, n is positive. But also notice that, so in some sense, right, this is biased, right? It's biased for the population min. But it goes to 0 as n goes to infinity. Okay, it gets closer and closer to a target as the sample size gets large. Any question? So, right, I mean, I'm not writing 0 here. Yes, that's a more advanced property of statistics called consistency. And what we're doing here is we're looking at something called the MLE, maximum likelihood estimator, all topics for chapter 10. And the thing that we will not discuss in this class even is that the maximum likelihood estimator is consistent for its estimator, meaning that it will asymptotically goes to whatever it's supposed to estimate as the sample size gets large. But that's a advanced statement that we don't state. I'll mention it when we go to maximum likelihood estimator. Yeah, but it's true. You just have to know what distribution you're looking at, or what estimate you're looking at, and what statistics you're looking at. If it's a maximum likelihood estimator, then yes, it will be consistent. So, right, I mean, never mind what I just said before. That was just explaining to Madhav. What the point I want to say here is that, right, comparing the sample minimum with the population minimum, right, you see this interesting observation, and right, is the bias gets smaller as you have large sample size. Any other question? All right, so now we got the sample min, right? We got the sample max. the sample median, right, is really what we want to get next. But actually, right, while we're at it, the concept we want to get is the sample, the order statistic for any k. Okay, so if you take the kth so-called, I guess, largest element in your order in your sample, right? What is the density of this kth order statistic, right? This is the kth order statistic, the kth largest value in your sample. What is its density? Okay. Now, does any one of you memorize this? Like you have seen it somewhere? If you memorize this, this is very good, actually. And as I'll show you, the memorization is the same as what we have talked about before, if you understand the idea. But just out of curiosity, does anyone memorize this? So let's start with, a naive concept. Before, right, we had some good success with looking at this kind of relation. Does it work here? Is it helpful to consider this kind of relation in this context for the kth order statistic? So to give you some picture, right? Suppose we have your minimum, right? And then your second one, so on and so forth. You have your kth order statistic somewhere here, and you have your max here, right? And I don't know, you could look at a value x like this, and you ask what's the probability that, right, k values of your sample is to the left of it, or you can consider an x on this side like this, and I guess here then you ask k plus 1 values, right, of your samples above it or something. All right, so you should try to contemplate this a little bit, all right, to appreciate the formula, because eventually, of course, you have access to a formula, but if you don't appreciate the formula, you may not see what's going on. So let me say this, right? Is it true that this statement, right? Let's take this statement, which is this picture. Is it equivalent to something like this? K values of the sample is less than or equal to x, and n minus k values is bigger than or equal to x. Is that true? Right? If the kth largest value is less than or equal to x, that means k of these values must be less than or equal to x, and n minus k, right, must be bigger than or equal to x. Or, let me make it even more clear, bigger than x. Yeah, right, I just corrected that. Yeah, but is that true, this statement? And by the way, right, you see, if you turn this into this kind of statement, then you can use the language that we were doing before, right? Turn into an and statement, and then, multiply it out. Is it true that this is the statement? No, it's not. Why so? Because, no, it's fine, it's fine. It's good to make mistakes. The error is on the k. It doesn't have to be k. Because notice, right, this picture I draw, is still the case if you have the k plus 1 like this and x like this, isn't it? This is still a case of the kth value, the kth order statistic is less than x. Yes? So if you want, it would be something like this, at least, at most. Do you understand? So at least k values is below x, at most n minus k. So in other words, right, you allow for this, but you also allow for the k plus 1, you know, order statistics less than x, k plus 2, etc. Is that okay? So this is the right statement. But you see that if you work with this statement, that's an or, meaning k values or k plus 1 values or k plus 2 values all the way. It will turn out to be a very messy business, okay, of how to handle this expression. Same thing here, right? You can see that this is not, it will turn into some statement like that as well. Okay, so what's the issue with this kind of statement? The issue with this kind of statements, they're a little bit too loose. They don't nail down the kth order statistics very well. With the max and the min, they completely nail down the max and the min. Why? Because the max being the max, right? Everything must be to the left of x if the max less than x. The min being the min, right? Everything must be to the I guess the right of x, right? If the min's bigger. For the kth order statistics, because of this, what you want to do is you want to kind of isolate the kth order statistic around x, below and above. Okay, so the picture is something like this. If you choose epsilon small enough, if you choose a small enough epsilon, okay, epsilon is just some small error. If you choose some small enough epsilon, like this, then within that band, the only sample value that should be in is your kth order statistic and nothing else. In other words, if epsilon is small enough, k minus 1 values of your sample must be to the left of x minus epsilon. N minus k values of your sample must be to the right of x plus epsilon. Is that okay? So the key difference, right, between this statement and this statement is that this nails down the precise value, the precise position of xk. That does not allow for some, you know, wishy-washiness of all the sample values in it. So that translates to something like this. So it's approximately, right, probability of k minus 1 values of the sample less than or equal to x minus epsilon. One value in between. And then n minus k values. Is that okay? And notice that this exactly, like, you know, get rid of the at least and at most. So you can convert this to an AND statement, but there's a combinatorics going on here, because, you know, these can be just any values you can choose. So in other words, there's some combinatorics going on like this. N choose k minus 1, 1, n minus k. Okay. k minus 1 values less than this, one value in between, n minus k values bigger. Any question? Where, right? And so I don't know, n choose, let's say this, will be n factorial over k minus 1 factorial. I don't need 1 factorial, I'll just write it down, and n minus k factorial. This is the multinomial coefficient. Okay. It just demonstrates how many ways you can pick exactly this combination out from n values. Any question on this logic? Any question on this logic? Okay, so what's the last step? The last step you want to do is to recognize that the density at a point will be the limit as epsilon goes to 0 of the probability that the random variable is in between that band. What's the idea? The idea is exactly the fundamental theorem of calculus. So here's x minus epsilon, here's x plus epsilon, here's your density. Okay. So this area under the curve is exactly what you mean by probability x in between those values, right? So if you, this is x. Obviously, right, this area under the curve is approximately the value of the density at x times 2 epsilon, for example. Okay. Oh, my bad. I think you need to divide by 2 epsilon because, you know, is the width is 2 epsilon. But right, so the point is, if you take this area, divide by 2 epsilon, and you squeeze epsilon goes to 0, then the value, right, will be converging to the density value at x. So the relevant for that to us is what? You divide both sides here by 2 epsilon. Okay, and send epsilon goes to 0. If you divide by 2 epsilon here, you get the density of the kth order statistic. Epsilon goes to 0 here, just gives you x. Epsilon goes to 0 here, just gives you x. This one gives you the density of the population distribution. So in other words, so divide, right, both sides by 2 epsilon. Send epsilon goes to 0. You got the density of the kth order statistic is n choose k minus 1, 1, and minus k. Probability x less than or equal to x raised to the k minus 1 times the density times probability x bigger than x equals, find here, n minus k. That's the formula. So eventually, right, you don't have to repeat the logic. This is the statement. But, you know, I want you to see the logic to see that, you know, this statement makes perfect sense. In other words, right, what does this density, what is the role of this density? This density exactly, right, establish that statement right there. Notice it's very intuitive. It says there is one value that you are at x or close to x. K minus one values less than x. N minus k values bigger than x. And you have to do a combination to get it out. All right. Any question here? Let's see how this applies, right? So this is the most general logic. And if you understand this concept, you can derive any other stat out of it. I mean, of course, this is the other stat anyway, but I'm saying the principle applies to any other situation you may want to care about. For example, let's revisit our max, right? I know we have derived the max, but let's try to use this logic. So what does the logic say, right? The logic says that you must have one value at around the exit. You must have n minus one value less than that. And then how many ways can this happen? This clearly can only happen in an n choose n minus one way, because you choose n minus one value to be less than that, right? Which is exactly n probability x less than or equal to x raised to n minus one. Okay. Same thing goes for the min. One value at that, around that point, x, n minus one value must be above it. How many ways can it happen? Again, n choose n minus one. Or, you know, this can also be n choose one if you want. Which one are you choosing? You're choosing that single one that goes into the max value. That's it. The rest goes to the other way. So if you want, this n choose one as well. Any question? Right. So again, the picture is here. Here's x, right? You choose one value here. And then n minus one values here. Here, right, the picture is x here, one value, n minus one values. So let me show you one thing, all right? Application of this idea. So this is easy because we have derived it. Application is your question on, let me see. Question 8.52, where they ask you to derive the joint of the min and the max. Okay, so let's say x and y. Where x refers to the min and y refers to a max. Let me just show you the logic, all right? It must mean that one value is at the min one value is at the max, n minus 2 values must be in between. How many ways can this happen? N choose n minus 2. And that's it. That's exactly what they ask you to establish in 8.52. All right. And that is the logic. By the way, this is super important because this allows you to compute the density of the range, where the range is the max minus the min. And you see how this is exactly connected to transformation of variables in your quiz 1. All right. So sorry for keeping you over time. I will stop here. If you have any questions, I'll answer. Otherwise, see you on Tuesday.
Do you mind if I ask a quick question?
Absolutely. Should the other term be no, Madhav, right? Let me answer, Madhav. No, because that's where you're confused, right? Here, thank you. They are all the same density, isn't it? They're all the same density of the population distribution. These are the same guys. They are the same guys, right? We just use y to denote the value of the max. That's the particular value of the max. But in terms of its density, right? The density it derives from, because they come from the same population, it's the same density. Does that make sense? It's the same density. So this x right here has no connection with little x. So if I want to make it a little bit more precise, maybe I should do this. I should do little x1 and little xn. So this will be little xn. This will be little x1. This will be little x1 to little xn. Do you understand? Yep. All right. Was it Aaron?
Yes.
Aaron.
So
what question do you have?
Yeah, we talked about at the beginning of the class how the max of the exponential is undefined, but for a lot of values
population max, right? Be careful there, right? The population max.
Right.
Yeah.
But for a lot of, since it's defined as 0, if x is less than 0, isn't for a lot of values of lambda, doesn't it, like we can find a maximum of that function? Like if we set lambda equal to 4.
Okay, let me recap your question because there's some lessons going on. So you okay, so let's put your question in context. x1 up to xn, IID exponential lambda, right?
Yes.
Okay, now what's your question? You want lambda equals to 4?
Yep, so if we choose 4 works.
Okay, so what is your question?
So just looking at the graph of that, because when x is greater than, yes, exactly.
So that will be 1 over 4 e to the minus x over 4. So looks something like, I don't know, again, something like this with the average at 4. Go ahead.
Since it's 0 for x less than 0, does that function not have a maximum?
Okay. I don't know. I think, right, that this is where I think your confusion is there are a lot of max going on, too many maxes.
Right.
What you're thinking of is the max of the density.
Yes.
Which, by the way, has nothing to do with the population max, which also has nothing to do with, right? Okay. But so when you say the max, is max of what? When I say max of the population, I'm talking about the max of the support.
Right, I see that now.
Yes, you're talking the max of the function on this support. And yet there's another max where we talk about a sample max, which where you line up
Right.
n values, right? So yes, actually the max you're thinking of is very important in the MLE, maximum likelihood estimator. It has a role,
Right.
right? But yeah, I mean max of what, right? Max of what?
Okay.
Max
But
density.
the tail of that exponential goes on infinitely long, so there's no
And by the way, right, I
actual
think
max.
this, even if you want to talk about the max of this function, I think it's at 1. Because,
Okay.
right, it hits 1 here when x equal to 0, and it decays there. So if you want to talk about max of this function very pedantically, it's 1, happening at x equal to 0.
Okay, but we're talking about the x values here that the
We talk
function
about
can
the
take
support.
on.
We talk about the support, meaning,
The support.
right? So the random variable being peculiar like that, right? The value of the random variable is on the x-axis. This
Right.
function only describes the likelihood that it's around this neighborhood, right? This function does not describe the value of the random variable in a way. It describes the likelihood of the random variable in being in that neighborhood, right?
Yeah.
In more advanced math, we call that measure, the measure theory. Measure.
Yeah.
But yeah, so don't confuse, right? The easiest confusion is to confuse this with the value of the function, the random variable.
Yeah,
The value
that's totally what I was doing. And so it feasibly can take on an infinitely large x, even though the likelihood's small of that happening. So
and
there's
that's
no
exactly
max.
what should happen, right? I mean, if you
Right.
have a very large likelihood of the value being large, then your function is not integrable. So the expectation is infinite, for example. Could happen, right? But you see most reasonable density. Oh, by the way, it's not even that. The density itself may not be integrable because, right, if you say that my random variable has a very large density of being large, then what's the probability, in general? Oh no, I think, yeah, the probability may not make sense, right? Because if you have a function pickup like this, then the area under the curve is not 1.
Is not 1. Okay.
Does that make sense? So
Yeah.
that's why you see that a lot of density, it must tail out at the end, which
Yeah.
makes sense in life too, right? How often you see large values. So
Right.
for the density to be 1, the tail of the density, sorry, for the area, right, for the total probability to be 1, the area of the density must tail out, right? Must decay at the end. Otherwise, again, you won't have mass 1.
Yeah.
Yeah.
Yeah, I was just getting those two mixed up. So thank you for clarifying.
Sure.
All right. Have a nice day.
You too. You too.